Okay, so for the first part of Kalman filters, you need to learn about linear least squares. And you've probably done linear least squares regression in sort of numerical analysis, or maybe your stats class or something like that, or maybe even Excel, you just right click the graph. But in order to do it for the Kalman filter, you need to understand how to do linear regression for matrices. Okay, so the example I'm going to do is I'm going to just assume a 1D problem that's linear. So I'm going to put angle of attack here, and I'm going to put lift coefficient here. And so this is linear, so it's got an intercept and it's got a slope. The intercept is CL naught and the slope is CL alpha. And so the x-axis or the abscissa is alpha and the origin axis is CL. Okay, so it's linear, so there's two unknowns that I want to know. Now though, I'm going to put it in matrix form so this works for anything. So the idea is that as I take data, I'm going to use a different color. As I take data, because there's measurement noise, I'm going to get a bunch of data points that look like this, okay? And each one of those data points is going to be y bar I. That's a measurement, okay? I'm going to take y bar I and I'm going to put it into a big matrix called y bar. And that's going to be y1 bar all the way down to ym bar, okay? And m is the number of measurements that I take, okay? Now, if this were a perfect world and there were no measurement noise, then obviously if I took my states, so my states in this case, see, I realize this is the x-axis, I'm doing an x vector, but this is a little bit different. So in this case, alpha is actually my abscissa, and x is my state. And so CL naught and CL alpha, those are my truth variables. And so x tilde is the estimate, CL naught and CL alpha. Those are the estimate of those two values there, okay? I need to make sure I get my notation right here, okay? And so if I took the equations here, there is a matrix H where if I take my state X and multiply it by H, I'm going to get my truth values Y, okay? Now the problem is that there exists no solution where H times X equals y bar. And the reason why that's impossible is because you have a bunch of data points that are all over the place. There's no way that this would be satisfied. So unfortunately, you need to add a V here, okay? And this V is your measurement noise, okay? Measurement noise, okay? Now this line, this black line here, is not actually the truth there. It's actually what I'm considering to be the regression equation, where that black line is my best guess at how that line goes through those data points, okay? And so in that case, it's saying, if I take my estimated state and I multiply it by this H matrix, and remember, this y bar is known, right? Those are my measurement equations. And then this H here is also known because it relates my states to my outputs. And so this is like an output equation. And so X is really what my unknowns are. And this is why I'm trying to estimate it with X tilde. So this point, say here, is y tilde I. And then this point here is y bar I. And so you can see the difference between my regression equation and my measurement is what I call delta y, okay? Where delta y is y bar I minus y tilde I. And let me make sure that I got the direction right. Okay? Delta y. Okay, I actually have it the other way around, which I'm not sure if it makes too big of a difference, but it might. So it's actually y tilde minus y bar. Okay? Alright. So So the other thing that we want to do is if we look at this and we say, okay, let's put this in our enlarged matrix form. What we have is we have delta big Y is Y tilde minus Y bar. Okay? Now, Y tilde, my estimate, my regression equation, is just H times my estimate of my state. Okay? And again, I mean, it's kind of confusing looking at all this, right? So you have H times the truth signal plus measurement noise is equal to my measurements. And this V here is totally random, right? It's basically all of my errors added up together. Okay? You could also do the Y tilde like this is HX. Hang on, let me make sure I got this right. You could also do, yeah, so now I'm seeing what I'm doing. You could also take your measurement equation and say, okay, well, instead of using HX, let's use H tilde. But in order to do that, remember HX tilde is your regression equation, and so you would have to add delta Y, where these are your residuals. Okay? So if you took your estimate of your state and multiplied it by X, you would get this black line here. And then if you added delta Y, that would be all of your little residuals. That would get your measurement Y bar. And then at the same time, if you took your truth signal and multiplied it by H and added your measurement noise, so that's the thing. Remember, the difference between your measurement and your regression equation, that's not your measurement noise. That's because your regression is your best guess. And so there's a difference between your residuals and your measurement noise. The idea is that you hope your measurement noise is low so that you're fitting the truth correctly. Okay? And so the way we proceed here is what we really want to do is we want to minimize a cost function. And what I really want to do is I want to minimize delta Y. Okay, that's what I want. And so what I can do is I can create a cost function J and say call it 1/2 delta Y transpose delta Y. And the reason why you do this is because this is quadratic, and quadratics have a specific minimum. And so in order to solve this, let me move this out of the way here. In order to solve this, what you want to do is you want to set partial J partial X tilde equal to 0. And that will minimize your quadratic. Okay? So in order, I'm going to see if I can do this on one board. If you do this out, delta Y is Y tilde minus Y bar. So Y bar is known. So, and let me make sure I've got my, like I said, I've got my notation correctly. I see, I have a typo, I'm sorry. It actually was Y bar minus Y tilde. Y bar minus Y tilde, Y bar minus Y tilde. And that doesn't really matter because we probably could have done it the other way, and since we're squaring it, we would have gotten the same thing. I just need to make sure I update this in my notes. But anyway, if we go ahead and shake this out, Y bar is known, so I can go ahead and just bring that Y bar down. And then Y tilde is HX tilde, so I can just put an HX tilde transpose Y bar minus HX tilde. And then if I carry out the, if I carry this out, I'm going to get 1/2 Y bar transpose Y minus, and you'll notice you're going to get an HXY minus a YHX, but all of these things are symmetric, and so really what's going to happen is you're going to get 2 of these, and now what you need to do is you need to make sure you have the right order when you take the transpose and things. So if you do the math, the matrix multiplication is kind of weird, but you're going to get X transpose H transpose Y. Okay, and then here you're going to get plus X tilde transpose H transpose H X tilde, like that. Okay, and there's your equation there. This is all factored out. If you take your partials of partial j, partial x, what you're going to get is there's no x tilde there, so that goes away. This term here, oh, I forgot to distribute the 1/2, sorry. So the 1/2 is going to distribute, you're going to get a 1/2 here. This 2 is going to go away because you're going to get a 2 from those and the 1/2 cancels. And then you're going to get a plus 1/2 here. Okay. So this one is going to go away because there's no x tildes when you take your partial derivative. And then this one here, when you take a partial derivative of x tilde transpose, you're just going to get h transpose y. And so you're going to get a negative h transpose y. And that's y bar. Okay? Plus, this is x tilde transpose h x tilde, which is really similar to if this were, what is it called? If this were scalar, it would be 1/2 x squared h, and that would give you x h. And so basically you get the same thing. The squared term comes down because you have 2 x tildes over here, and that cancels the 1/2, and you're just going to get plus h transpose h x tilde. Okay? And so you set this equal to 0, and what you get is that x tilde is h transpose h inverse h transpose y bar. And that will essentially give you the best fit line that minimizes your residuals. I'm not sure if you've ever seen this in stats or any analysis or anything like that, but this is the full derivation that was originally done by Gauss and Markov, I think. And so here is your estimate x tilde. Again, if you, absent of model noise, absent of measurement noise and absent of model noise, you would get a perfect solution. But what happens is that you have an over-constrained problem in the sense that you have more measurements than unknowns. It's typically assumed that n, the number of measurements, is greater than n. So n here in this case is 2 because you only have 2 unknowns. And if you had 2 measurements, you get a perfect line and it wouldn't worry about it because h transpose h would turn into a 2 by 2 and you would just get the inverse and everything would work out. But typically what happens is that you have like 20 measurements. And so when you do h transpose h, you actually deprecate those solutions. And you'll still get a 2 by 2 here, but you lose information. And so what you're essentially doing is trying to project like a n-dimensional vector into a n-dimensional space. Okay? Alright, so that's linear least squares regression using matrix multiplication. And after this, I'll show you weighted least squares regression. I think I'll go ahead and do that on the next board here because it's pretty similar, and I'm not going to show the derivation for that. So let me take a photo of this real quick. Okay. Okay, I'm going to upload nonlinear controls. Okay, I'm going to erase the board. Okay, so weighted least squares regression goes like this. The idea is that instead of saying that your cost function is equal to, for the linear least squares regression, you assume that j was 1/2 delta y transpose delta y, and then your optimal solution was h transpose h inverse h transpose y bar. Okay? In weighted least squares regression, what you do is you use a cost function 1/2 delta y, same thing, transpose, but then you put this W matrix in the middle, where W is typically a diagonal matrix that estimates all of your, you could have some correlation terms if you wanted to, but basically what it does is it says, which one of those measurements do you believe? Like, is it possible that in the first 10 seconds, your sensor is really inaccurate, And so the first 10 measurements you don't want to believe as much, but you still think they're pretty accurate, just not as accurate as the other ones. You could weight the other measurements better than the others. Or perhaps you swap sensors and you want to, believe one measurement, one sensor over another. This is a way where you can scale that. The derivation is almost the same, and you basically just factor everything out, take a partial derivative, and just to spare you the derivation, what you end up getting is you get x tilde is h transpose w, h inverse h transpose w, y bar. Okay? Now the reason why we do weighted least squares is because what we're going to do is we're going to assume that the expectation, right? So this is sort of like a mean of covariance. I'm going to assume that the expectation of my measurement noise is equal to R, okay? And so typically what we do is we say, I'm going to make W equal to R inverse. And so I'm probably going to talk about this again in another video, but the idea is that you assume that the expectation of your model noise is R, and then you set W equal to R inverse, so it's inversely proportional. What you end up getting is that x tilde is H transpose R inverse, H inverse, H transpose R inverse, Y bar. Okay? And this is getting us closer and closer to the common filter. So we've got linear least squares regression, weighted least squares regression, and now instead of weighting it based on just a random matrix W, we're using our expected value of our measurement noise. And so the idea is that if our measurement noise is super, super, super high, then W is going to be super small. Okay, and so basically we're going to weight them lower because we don't want to believe them because our measurement noise is so high. Okay? From here we're going to move on to a priori knowledge of our state, and then after that we're going to move to sequential least squares regression. Okay, so I'm going to pause here and make another video for the a priori knowledge. All right?